Hello, welcome to Unit 7 Part B, the very last video you will need to watch for this whole thing, so congratulations on making it to the end. I appreciate your patience with this, but it is a way that gives us more time in class to practice and go over problems, so you've made it to the end though, so good job. Part of this unit is mostly about global warming, which of course is of great importance to an environmental science course. And just to review the greenhouse effect, and it's exactly how a greenhouse works, is that uh, sunlight, visible light, is allowed to go through the walls of this greenhouse, and it makes the inside warm, and the heat is then trapped inside by this plastic or glass or whatever the greenhouse walls are made out of. And this is basically how the greenhouse effect on the planet Earth works. So number one, electromagnetic radiation, light, mostly visible light with some ultraviolet, is absorbed by the Earth's surface, and then the electromagnetic radiation, as the Earth's surface warms up, that's re-radiated back towards space. It doesn't all go directly back into space, is in the form of IR light. And the infrared light is capable of interacting with the gas molecules in the atmosphere. The visible light passes through the gases, for the most part, completely unabsorbed. And then the infrared light that is released by the Earth's surface does interact with the gases in the atmosphere, and specifically the greenhouse gases. Some of the heat energy in the IR that's radiated back into space, towards space, is absorbed by several gases which do not absorb heat energy from the shorter wavelength visible light. Again, but they do interact with the infrared light. And this is how the Earth is heated by the sun, and this is the greenhouse effect. By the way, it's a good thing, because the greenhouse effect, without it, at nighttime the Earth would be completely cold, losing all of its energy. So the greenhouse effect allows the infrared light that's re-radiated back towards the atmosphere to kind of bounce around, and the Earth doesn't get completely chilled to absolute zero every night. So greenhouse gases, which are both natural and anthropogenic, carbon dioxide, of course, is the one that gets all the attention. Uh, some of it's natural. The majority in the atmosphere is natural, but it also comes from burning fossil fuels and also from deforestation, meaning as you cut down trees, and whether they decay or you burn the trees, that will just release the carbon dioxide back into the atmosphere. 30% is the increase caused by humans of the natural levels of CO2, and we'll look at some graphs later. And the average atmospheric residence time is 500 years. So that's sort of a chilling statistic, because even if we were to cut our carbon dioxide production, which we are nowhere near doing that, even if we were, it would be a very long time before things got back to normal. Water vapor, of course, the largest amount of it is natural, but it's also a product of burning fossil fuels, industry, oceans and lake evaporation. Anthropogenic increase, here again it says 30% in 500 years, but it's the process of removing water from the atmosphere through precipitation is a fairly quick process. So even if we stopped all the anthropogenic sources of water vapor, things would be back to natural level really within just a few months, not 500 years. That's how long a water molecule could stay in the atmosphere. Now, methane, there are some natural sources. Methane is just a very small organic molecule, and it is the product of a lot of types of decay. So anytime something is decaying, whether it be manure or feces, dead animals, dead plants, methane is generally going to be produced. When they cultivate rice, this actually produces methane. Cattle and sheep ranching, through their manure. Landfills are big sources of methane, as are mining and fracking. Anthropogenic increase of this is pretty substantial, that we've more than doubled the amount of methane in the atmosphere. Fortunately, it's a small number to begin with, but methane is even more interactive with infrared light than carbon dioxide or water are, by quite a bit. This molecule, it will not last in the atmosphere as long, only 7 to 10 years, because it will get oxidized by either oxygen or other oxidizing agents in the atmosphere, ozone, and other molecules like that will react with it and turn it into carbon dioxide and water. Ozone, some sources of that, their natural source, of course, is the ozone layer in the stratosphere. Industry and agriculture, so fertilizers, and of course, ozone is created as a byproduct, a secondary pollutant from the driving of cars, as we talked about when we mentioned smog. These ones are greenhouse gases that are exclusively anthropogenic, meaning there are no natural sources. Chlorofluorocarbons and halons. Halons are very similar to the chlorofluorocarbons. Halons are used in firefighting, fire extinguishers, and things like that, specifically for computer rooms, because the halon is not messy, and it will, if you can put a fire out with it, but it will turn to a gas and completely leave the computers unharmed, provided they weren't the object on fire. Whereas a traditional fire extinguisher is filled with a powder that would ruin pretty much any computer that it came in contact with. Nowadays, they replace the halon fire extinguishers with carbon dioxide ones. So these chlorofluorocarbons, they use them in coolants, refrigeration, and air conditioning, and they used to be used in the production of styrofoam. And these are very stable molecules and will live in the atmosphere for around 100 years. Nitrous oxide is N2O, not the NO or NO2 that is traditionally coming from car engines, but the source of these are from industry and agriculture. And if you recall, catalytic converters actually sometimes produce this as a byproduct of when they try to remove the NO and NO2 from a car's engine exhaust. N2O can live in the atmosphere for around 140 to 190 years. All right, so back to talking about the interaction between the sun and the radiation that we receive from the sun, and plus what the Earth re-emits. They call it the radiative balance. So the balance occurs when the heat energy from the UV radiation and visible, this doesn't say it, but the visible and UV light absorbed by the Earth basically equals the amount of heat re-radiated back by infrared radiation. There is, when you look at one day to the next, it's pretty much stating that all of the energy that we receive from the sun in a day will also be lost by the Earth back out into space. And that is very close to a true statement, that all of the energy that we get from the sun every day is also re-radiated back from the Earth in the form of infrared light. And if it was exactly true, then there would be no global warming. But the amount of energy we get from the sun every day is tremendous, and the amount of infrared light that the Earth returns to space every day is tremendous, and almost equally as tremendous as the amount of light that we get from the sun. But with respect to global warming, there's a tiny smidge that the Earth will retain on a daily basis, but it would be such a tiny, tiny, tiny fraction of just 1% of that amount of energy every day. So usually the Earth heats up or cools down somewhat over time due to changes in the amount of greenhouse gases. So if there's an increase in greenhouse gases, the Earth heats up, and if there's a decrease in greenhouse gases, the Earth cools down. We're talking about more in the geological time scale, a long-term time scale. There's been ups and downs in the Earth's temperature, and through ice core samples and things like that, they're able to actually determine what the composition of Earth's atmosphere was. So there have been times in Earth's history where the Earth was very cold or very warm compared to today, and they have been able to determine that there are corresponding changes in the amount of the greenhouse gases during these times. Carbon dioxide and methane in the atmosphere have changed in the past due to volcanic activity, decreases in plants, meaning if there's a period where a lot of plants and trees on the Earth if the total biomass is decreased, then you wind up with more carbon dioxide in the atmosphere, and that's been shown to cause warming in certain times. This does bring up a question that how do we know that the warming of the Earth going on right now is not due to one of these natural cycles or something that happened to the Earth in the past on its own? And the very simple answer to that is that all of these, the ancient Earth's time scale, the temperature changes that have happened in the past happened over a much longer period of time than the warming that we're seeing right now. So there's been a history of 5 mass extinctions on the Earth, and one of them was caused by the meteorite that killed off the dinosaurs. But the other ones were all caused by climate change, and they were not a overnight process. The warming of Earth due to global warming now has been tracked for about the last 100 years since the Industrial Revolution. There's a very strong correlation. There's never been a time in Earth's history where the temperature changed so much in just 100 years. So, in the other some of the mass extinctions that have occurred in the past, there have been similar changes in temperature, but they take thousands of years, maybe millions. So the Earth's greenhouse effect, again, just to put it into a image here, the Earth is absorbing incoming solar radiation. Insolation is what they call it, in the form of mostly visible light with some ultraviolet. The sun beats on the ground and makes the ground on the Earth hot, or the water, not so much the atmosphere, but then as the ground and water get warm, they re-release heat in the form of infrared radiation. Some of it does go directly back out into space. Other of that infrared light bounces around between the greenhouse gases in the atmosphere before it eventually finds its way out. And for the most part, every day it's an equal amount of energy coming onto the planet as there is leaving it. But that would, even with global warming, it's just a very tiny fraction that the Earth is absorbing more than it's re-releasing. This graph shows you, so really since the last few ice ages, which seem to have a frequency of about every 100,000 years, and these are from ice cores taken from Antarctica, and they've been able to correlate. They use the isotopic ratios of oxygen 18 and oxygen 16 in water that's frozen. So when they look at the ice, they can actually determine, because we know what the percentage of oxygen 16 and the percentage of oxygen 18 should be on the planet at any point in time. But during cold periods, when the Earth is colder, the oxygen 16 is going to evaporate at a faster rate than oxygen 18. And during a warmer period, the oxygen 16 and 18 ratio is going to be a little bit closer to equal. So that's how they determine the temperature. And the carbon dioxide concentration is taken by the little bubbles that are trapped in the ice cores. They can sample them and directly tell the CO2 concentration. So as you can see, the pattern here is that there's a rapid increase in temperature followed by a slow cooling period, and then a rapid increase. And we are sort of at the top of one of these interglacial periods. Interglacial meaning between ice ages. We're at a warm point, and the CO2 concentration is also high, like it should be. But if you notice these numbers, on the right-hand side, these would be the parts per million of carbon dioxide. This graph actually stops at 300, and it's a couple years old, this graph. And recently, it's been making the news that they've been recording concentrations as high as 400 parts per million, which would be way up on the graph and above the page here. And it's been a couple of years that the very first reading of 400 parts per million was made in Hawaii, and now these readings they're not every day that high, and there is some seasonal variance and things like that. But for right now, there's very often they're seeing the readings of 400 parts per million. So you can see that the carbon dioxide concentration, even by direct measurement of modern techniques, it's definitely showing an increase. Consequences of global warming: changing disaster patterns. Weather-related disasters doubled over the last 20 years, and then there's also an increase in what they've labeled as small and medium-scale disasters. So how they quantify these things is kind of grim, but something like a major hurricane might be, a large-scale disaster, whereas maybe some just a pocket of tornadoes or something is medium to small scale. There's more uncertainties in this, but the lines at the bottom are showing geophysical, which would be earthquakes, and there's not really any change in the number of disasters in this time period. Epidemics such as insect infestations are kind of up and down a little bit, but then the hydrometeorological, meaning hurricanes, tornadoes, and things like that, are increasing in the last 20 years. So there is definitely a disturbing trend there. More warm days means there will be more heat waves and a higher death toll amongst the elderly and disabled. Those are the ones who will suffer the most from hotter weather, and also an increased risk of forest fires is shown with an increase in temperatures. And this seems contradictory, but flooding and from more intense rainfall is also associated with global warming. As the oceans get warmer, the water will evaporate quicker, and that will put more moisture into the atmosphere, which of course can then fall as increased precipitation. And as there's more flooding, this creates landslides, which adds to the degradation of the earth and kind of really accelerates erosion. The water will tend to be polluted as land pollutants that are trapped on land will get washed into waterways, and harvest farming will obviously be destroyed if plants wash away. But on the other hand, in different parts of the world, this can actually create more droughts by making the land hotter. So you're talking about areas that are already arid or semi-arid could be made even drier. You wind up with too little water for drinking. Food security is threatened, meaning people will not have access to enough food. Um, and the potential impact on conflict and migration. If areas start to run out of water, people will start to move in large quantities from the dry areas to the wet ones, and they're not always welcome when they get there. So the tropical storms, including things like hurricanes, will become more intense and also with a greater frequency. But the intensity is reflected in higher wind speed and an increased rainfall. Sea level will rise. This map of Europe is showing in outline the present coastlines and saying that if the global warming continues, the flooding of coastlines will happen here and make the new coastline pretty far inland. You'll see entire countries like Denmark and the Netherlands would be completely flooded. A very large part of England, which is where most of the population of England lives, is in the southern part near London, areas that would wind up underwater, but huge amounts of Europe, and of course there's similar patterns in the United States. And the sea level rise will bring large coastal areas will be at risk. Saltwater intrusion will threaten the water supply and thus the food security. So remember, groundwater can be contaminated by saltwater. So if the coastline moves inland, it can saturate and percolate into the land and actually intrude salt water into the underground groundwater that serves as drinking water for coastal communities. And the impacts are already being felt, especially with the higher storm surge. So it's not as though it just increases a couple inches every day or even millimeters, but the impact of a sea level is most seen during a storm. And so a similar sized hurricane that hit 20 years ago would not have caused as much damage and flooding as the same sized hurricane that would hit the same region now as the sea level is rising. Other effects of the sea level rise: erosion at the coast, loss of property and coastal habitats. People tend to like to live near the water, and when they get there, they build very expensive homes. So that will be a dramatic increase in property loss. Losses of fish and shellfish catches, especially shellfish that rely on living at the bottom of shallow water. Loss of cultural resources, and of course tourism and recreation of the shore and water areas. And also loss of agriculture and aquaculture because of decrease in water and soil qualities. You can find very many pictures of this that show how the glaciers are being impacted. This is an example of an alpine glacier, meaning one that forms in the valley of a mountain. And in 1978, we're not talking ancient history, the glacier comes all the way down to the bottom of this photograph, and then somebody went back to the same exact spot, took the same exact picture, and the glacier is back by several hundred feet. And this is not just the fact that that it's evidence of global warming, but it actually impacts the communities around here. This one, for example, is in Peru, and the glacier would melt in the summertime, not all the way, just slightly melt, and it would provide fresh water for the people that lived here at the top of this mountain. And now, as the glacier is melting, there's less of a supply of water, and sometimes you can see a little lake here that's formed, and that's called a glacial lake. And those occasionally there'll be a breakthrough somewhere in the earth that's holding back that lake. There's some sort of earthen dam, and then you wind up with what they call an outburst flood, and the frequency of these is increasing. Um, Health and climate change, there would be a shift of diseases to new areas. You see the mosquito here. When you have more flooding, you're going to wind up with a larger mosquito population, and of course the diseases they carry, malaria, West Nile virus, and there's several other mosquito-borne diseases. And with higher temperatures and humidity or drought, you're going to see more of these types of diseases. Other impacts, you see a change in the range of species. You already see some species of animals are moving north to find their ideal temperature, because they're where they normally live, that area is getting warmer, so they continue to move north, and it's causing population declines. Really, it's a loss of their habitat. Air quality is decreasing. Humans are moving away from equatorial areas because it's getting too hot, but also there's a lot of rainfall at equatorial areas, and that would be increasing, leading to more flooding. And remember, the equatorial areas actually have poor soil quality due to the large amount of rain they get. So if they get even more rain, they're going to have even more soil quality. It'll make growing food very difficult. Of course, the loss of biodiversity and an increase in extinction rates. And some people say we're on the verge of the sixth mass extinction, and what makes this one special is it's caused by humans. The release of methane from these clathrates, which are the frozen water ice that traps methane inside the crystals of water that form at very cold temperatures and very high pressures. And these are deposited in coastal areas and also in the permafrost. As the permafrost is the tundra, the land that's frozen all year round, but if it comes to as the earth warms in the summertime, it might be warm enough to melt the ground in these areas, and then the clathrates will release the methane, and then methane itself is a greenhouse gas, and this will just make global warming even worse, which would of course make it even warmer in these areas and allow for more methane to be released and make global warming even worse. And this is called positive feedback. And despite what you think the word positive means, this is a bad thing. Positive feedback means that the feedback is positive. It's contributing to the problem. Another form of positive feedback is that as global warming occurs, the earth gets warmer, more water will evaporate, so you'll have more water vapor in the atmosphere. And remember, water is also a greenhouse gas. So as the earth gets warmer, more water evaporates, and that will lead to even more global warming. And of course, then more water will evaporate and so on. So that's another form of a positive feedback loop. So reducing climate change. What do we know? The level of greenhouse gases in the atmosphere have increased, causing the Earth's temperature to rise. One greenhouse gas in particular, carbon dioxide, has steadily increased over the past century due to human activity burning fossil fuels. And we know that emissions have a significant impact on the world around us. So how can we reduce the amount of carbon that is emitted? And globally, CO2 emissions are expected to increase 2% annually until the year 2025 at least. And if you look at this, the total world, you see just now, even knowing what we know that we're the problem, we know what we're doing to cause it, and yet we just can't stop. And now you can see that industrialized countries, the so-called wealthy nations, are trying to make an effort to decrease, but the developing countries, where their concern is more about economics, if you have a poor population, especially if people are starving, you got to sit there and say, what's more important to us, the environment or the economics, when it is a now problem, whereas global warming is a future problem. So emerging economies, meaning the poor countries that are starting to improve, they will consume more fossil fuels than the developing world. And China and India, as their economies are continuing to progress, they will have emission increases of 3% per year, whereas the world as a whole is about 2% increase. But as you remember, the developing countries do represent the majority of the population. All that being said, the United States produces 1/4 of all carbon dioxide emissions. So that's by far the biggest problem. So just to stabilize current global warming, we're not even saying to decrease it, but just to slow it down, at least to stabilize and not increase carbon dioxide concentrations in the atmosphere, we'd have to decrease methane emissions by 8%, which doesn't sound like a big deal. Decrease the N2O emissions by half, that's kind of tough, but decrease carbon dioxide emissions by perhaps as much as 80% due to the long time that carbon dioxide remains in the atmosphere. This won't happen in my lifetime or yours. We won't come anywhere close to that unless somebody comes up with a way to make a car that can run as reliably and cheaply as a gasoline car. But right now, there's nothing that comes close to that that we're going to switch to anytime soon. So strategies to reduce dramatic climate change: increase the fuel efficiency of cars, use renewable energy, find chemical substitutes that are not greenhouse gases, saying to use chemical substitutes instead of the chemicals that we use now that we know are greenhouse gases, such as the chlorofluorocarbons. So to find suitable substitutes. Slow the rate of deforestation and encourage reforestation, meaning go to areas where they used to be forests and they've been cut down, and try to turn them back into forests so that trees will grow and sequester some of that carbon. Reduce the amount of nitrogen-based fertilizers and use conservation tillage. Remember the N2O and the total nitrogen amount in the atmosphere is part of that is based on nitrogen-based fertilizers. And support treaties and protocols that require reductions in greenhouse gases. Other nations have been willing to do that, but the United States was the one that creates the most opposition amongst the industrialized nations. Relevant laws is the Kyoto Protocol is the most famous one. So this was a UN Convention on Climate Change to reduce greenhouse emissions. The treaty took effect in 2005 after Russia became the protocol became official when 127 nations would ratify it. The United States will not ratify the Kyoto Protocol, and it only requires the rich nations to reduce emissions, but does not require the poor nations to do it. And that was one of the main complaints amongst people in the politicians that said don't ratify it, is that China is making a lot of our products that we buy in stores, and in doing so, they're making their economy's growing and they're producing more greenhouse gases. And China is reluctant to change anything because when they are pressed on it, they say, "Hey, the rich nations have been living a good life for a long time, burning all their fossil fuels, and we want to experience that too." So, of course, other countries resent the U.S. because we do emit 20% of the greenhouse gases, or 25, depending on how you look at it. And of course, then other nations are going to be less likely to want to go along with it if the largest producer of greenhouse gases doesn't want to go by this protocol. The nations that have agreed have actually increased their emissions by almost 8%. So then you got to even question the effectiveness of it. So that's it for the greenhouse gases. The last part to this is the loss of biodiversity in terms of what's changing in the globe. The number one cause of the loss in biodiversity is the loss of habitat. So this is the greatest cause of biodiversity loss. In the prairies, which are those grasslands, 99% of them are gone, and grassland bird populations have declined by anywhere from 82 to 99%. The biggest target seems to be the temperate grasslands as they're converted into mostly agriculture. Humans alter, degrade, and destroy habitats. It's what we do. That's our thing. Farming simplifies the communities and reduces biodiversity. When you change even something like a grassland into a farm, you're replacing all the native species with one crop. So, of course, that would be a change in biodiversity. Grazing, allowing animals to graze on land, it modifies the grassland structure and composition. And the clearing of forests, so this is not the grasslands, but some places forests are removed, and you're getting rid of the resources that the organisms need the native species. So you're also talking about clearing a forest usually to put in a farm will also greatly decrease biodiversity. Damming a river for hydroelectric will turn a river into a reservoir, and that will reduce the biodiversity from the river because now the water will be warmer. Instead of cool flowing water, you have warm stagnant water, and it's a different species that tend to live there, but you'll be wiping out the cool water species, and maybe the warm water ones don't have a way to get there. So that's definitely a decrease in biodiversity. Urban sprawl means the growing of a city, making the boundaries bigger as far as where there's a high density of population. And as urban areas spread out, they tend to replace the natural ecosystem, pushing out all the native species. Of course, the generalist species benefit, like rats and cockroaches that we view as pests, because they're the ones that did not leave. Habitat fragmentation. This is a type of habitat loss. This is the gradual piecemeal loss of habitat where you have a large chunk of forest and then you start taking bits and pieces, maybe taking them to farms, building roads in between small cities until what you have is a bunch of little, what they're calling landscape level, little patches of green, maybe like parks or small woods or forests or something like that. But then with the fragmentation, a lot of species will not cross over from one of these little islands to the next, and that will definitely threaten species. Habitat loss occurs in every biome, and that's what the headline says. But if you look at this, it looks as though tundra, nobody's after the land that's frozen all year round. But of all these biomes, they're all being impacted. So the grasslands are the ones that are most at risk, having lost already, depending on the stat, if you're looking at the United States or the world as a whole, but well over 70% of temperate grasslands are gone. Converted mostly to agriculture, used for grazing too, because if they don't get a lot of precipitation, it actually works better for grazing than for letting animals graze than it does for growing crops. 40% of Asia's tiger habitat has disappeared just in the last decade. But if you look at this, the temperate grassland, the chaparral there's significant decreases here also, yeah, but the chaparral does not have the huge amount of land mass that grasslands and deciduous forests have. So you can see, though, the temperate grassland and temperate deciduous forest, these are huge percentages of the land area, and huge percentages have been converted into other land use. So the temperate grassland and temperate deciduous forest would represent a huge decrease in biodiversity. But the point is, all of these have suffered. You would think, tropical rainforest is something that would have suffered greatly, but the thing that saves them is the poor soil is not very good for farming. Overuse, so the best example is overfishing and removing the species of fish, and left to our own devices, we would probably fish many species to extinction without regulation. So overharvesting, overuse, and overexploitation, which would apply more than just fish. For example, overhunting, of course, overfishing, and destructive harvesting practices, using cyanide or dynamite in water to go fishing. But then there's also illegal trade and exotic pet industry. Overharvesting does cause biodiversity loss. The ones that are vulnerable are those K-selected. These are the ones that have few offspring and take a long time to mature to get to an age that they can reproduce. These animals are large generally compared to our selected, but they're also fewer in number. They live for a long time and have few young. So to take away one animal means that you're taking away one animal could have an impact on the amount of reproductive possibilities. Siberian tigers hunt it without rules and regulations. So there's powerful economic incentives increase the poaching, and it's just in an area where the law is not does not have an effect. Other species are affected, such as whales, gorillas, and shark, and this is troubling. The oceans contain only 1/10 of the large animals that they once did. It's humans only that are impacting this. And biological diversity declines primarily due to the factors here. The biggest thing is habitat loss, and this is a direct cause. And you see increasing economic activity, increased use of technology, and social, political, and cultural factors. And these are indirect causes and direct causes. So the biggest indirect cause is the increase of human population. The biggest direct cause is changing of the land use, loss of habitat. Introduced species will also affect it. The fungus that destroys the American chestnut was introduced with a shipment of nursery items from China in 1904, and so it's actually considered an exotic species, and the American chestnut was nearly wiped out by this fungus infection. So invasive or introduced species also lead to a biodiversity loss. Sometimes it's accidental, like releasing of exotic pets or weeds or these zebra mussels. Sometimes it's intentional, where people bring from one area, they grew a crop with success, and then they take it to another area and they find that it starts to grow in the wild and might start to exclude native plants. And the new species generally do not have predators or parasites or competitors, and they can displace native species. And some of the examples here, the European starling, when you see these giant flocks of birds, even in New Jersey, and when you look at the flock flying through the sky, it looks like there could be tens of thousands in a single flock. And it's a really impressive sight, but then you got to remember they were native to Europe, and they were actually introduced in New York City. Just 100 of these birds were introduced by Shakespeare enthusiasts because they wanted to bring every bird that was mentioned in a Shakespeare play into America. So within 75 years, they were found everywhere in North America. So other things, gypsy moth and brown tree snake was introduced to Guam, an area that really didn't have this type of predator, and it kind of wiped out a lot of native bird species. And there are, of course, other examples. Disease, the Dutch elm disease. Elm trees used to be a lot more prolific, and it was first identified in the Netherlands, and that's why it's named the Dutch elm disease in 1921. It spread to the United States in 1930, and now it's throughout North America, and more than half the elm trees in the United States have been wiped out. Endangered and extinct species, pretty much due to a human interaction, the dodo bird. It's kind of a funny name, but the reason it was stupid is that it wasn't afraid of humans, and look what it got it. So for any animal not afraid of humans, it might lead to extinction. And passenger pigeon is another famous example. Endangered is just a species that is in immediate danger of becoming extinct and needs protection, whereas threatened is a species that is likely to become endangered if not protected. The ways that a species becomes endangered, number one is habitat loss. Number two, the unregulated killing or collection, or illegal, which would be poaching, pesticides and pollution, competition, disease, and predation. So biodiversity hotspots. This is an international approach that's intended to identify parts of the world that are considered these biodiversity hotspots, and they support a great number of endemic species, and these are species found nowhere else in the world. So an example of a lemur is found really just in a very small part of the world. So to receive this, for an area to be named as a international biodiversity hotspot, it must have at least 1,500 endemic plant species, and it has to have lost 70% of its habitat as a result of humans. And Madagascar has lost 90% of its forest, and illegal logging continues to threaten the lemur, this cute little fellow right here. So Madagascar has received this designation. And here's all the areas in red which have been designated. There's 34 total areas. You can see even in the United States, Southern California has some uniqueness to it. Pretty much all Central America, and the far western part of South America. So the Andes Mountains is kind of what this red line is tracking. The Andes are very close to the west coast here. A big part of the Amazon, and you can see other areas in the world such as Southwest Australia and other areas like that. So the stat here is that 2.3% of the land surface contains 50% of plant species and 42% of vertebrate species, at least the terrestrial ones. So especially areas near the equator tend to have more biodiversity. And what they're saying is that 50% of plants are only found on 2.3% of the Earth's surface, and 42% of vertebrate animals. So another idea here is community-based conservation. Developing nations often do not support the conservationists from rich nations. So if what they're saying is that people in poor nations don't always welcome environmentalists that come from rich nations trying to preserve areas, same as an outsider who is more focused on the environment than the poor living conditions that these people might be living in. So anyway, the community-based conservation is when a biologist will partner with the local people and make them feel like stakeholders and try to get them to protect their own land and wildlife. They offer education, healthcare, and development aid, and people are retrained to protect the species, the native people, the people that live there. Local resources can be sustainably managed. So that is the end of this, and you made it to the end. You are now ready to take Quiz 7 Part B, and that is the end of these videos. I appreciate your patience, and good luck to you. I will see you in class.